So good morning, everybody. Let me introduce you. My name is Nicholas Andika Harusasongko, and this is my student number right below on my uh, name appeared on the screen. So today I will explain to you how to solve some mathematics problems in terms to accomplish the midterm examination of mathematics for economics 2. So the table of content. In this presentation, the content consisted of three different questions that within those questions is basically contain three different materials. The first question is contained about optimization, and the second question is about constraint optimization, and the third one or the last one is about Kuhn-Tucker condition. So let's move on to the first optimization, the first question, which is the optimization. So there is a given question, which is, in the model of discriminating monopoly with an output quota, show that if marginal cost of production is constant, there is no effect of the imposition of quota in country 2 on price and output in country 1. Explain this result. So for the fundamental concept of this question is that profit equals to total revenue subtracted by total cost. And also there is a statement that marginal cost of production, or the MC, is constant at C. After we know the fundamental concept, we can assume that the total revenue or price is P1Q1, which is the formula of total revenue itself, plus P2Q2. Because of the MC is constant at C, then we will have no advance or further formula of the marginal cost itself. So we just simply define it as C multiplied by Q1 plus Q2. So the function, the optimization function is the maximum or the optimal function equals of these notations equals to TR minus T7, which is P1Q1 plus P2Q2 in C in minus C open bracket Q1 plus Q2. We get this by substituting this concept, or I mean this equation, and this by this equation. So let's find the derivation of pi with respect to Q, R, country 1. So this is called as the first order condition. The first order condition is just the same as the partial derivatives. However, the derivation here is works as but the distribution of multiplication. So this derivation, we just want to distribute it into each of variables or each of functions. So we got it here, and after we found or distributed the derivation here, we just want to make an adjustment by knowing whether the derivation is functionally working or not. So in the first one, we know that this is working, so it is valid, and this is working. Oh, I'm sorry, this is because this is, you know that the dou Q1 over dou Q1 can be stated as 1, so this is only P1, and plus dou P2 over dou Q1 multiplied by Q2 is not valid, so we entered or we define it as 0, and dou Q2 over dou Q1 multiplied by P2 is not valid either. It's not valid either. So what we can find for the last one is dou Q1C over dou Q1 plus the Q2 over the Q1 is not valid either. So, oh, sorry, this is valid. So we found this as C. So the end product of this calculation is do P1 over do Q2 multiplied by Q1 plus open bracket of P1 minus C and then close bracket equals to 0. It is also the same with the product of country 2, which we stated as do pi over do Q2 equals to this function. And we want to distribute this derivation just like the same as the first function that we have done before. And then we have to make some adjustment, and then in the end product of these functions or this calculation is this. So after we found this, sorry, I'm sorry. Okay. So after we found out of these two equations, we can simply conclude it. So the conclusion is, since the marginal cost of production is constant, the function is not being dependent by the output. Whenever the quota of country 2 is imposed, it cannot affect the optimal output of country 1. Vice versa with the country 1. Whenever the quota of country 1 is imposed, it cannot affect the optimal output of country 1. Thus, the profit output or the maximization will not be satisfied. So that is the solution for the question 1. Let's move on to the next question, which is the constraint function. So the given question is, the consumer has the utility function of u equals x1 of, you can see on the screen and here, where C1 and C2 are interpreted as minimum amounts of the goods required for subsistence. Derive demand functions, discuss their properties, and compare them with the demand function derived in the Cobb-Douglas example. Sorry. Okay, so let's move on to the solution. We know that we have been given of the consumer utility function, which is stated in the question, and then we have to make we have to know the constraint function itself. So basically, it's just y equals to p1 x1 plus p2 x2. We know that this is also similar with the question number 1. That p1 x1 is the total revenue of product 1, and p2 x2 is the total revenue of product 2. So we want to make a subject as a 0. I just move this these variables to the left, and we obtain the y minus p1 x1 minus p2 x2 equals to 0. So after we found this, we want to make the Lagrange function. Lagrange function is basically okay. I'm using L, but you can do whatever you can use whatever you want. So I use L equals to u plus lambda multiplied by the constraint function. This is the utility function. So I want to substitute this by substituting this into this, and lambda multiplied by our function of this. And then you want to distribute the lambda of its variables of constant function. Later on, to proceed the solution, to proceed to the next step, we have to make the partial derivatives of each variables. So the first one, I want to make the derivation of L with respect to x1. So yeah, we just can simply calculate it by the concept of derivation, uh, partial derivation, I mean, and we obtain this function, and you need to equate it into zero, and you classify this as the first function, and then do it the same derivation of with respect of x2, and equates it into zero, and I classify this as the second function, and the third one is the derivation of L with respect to lambda, which is back again into the constraint function, and we classify that as the third function. So we know that lambda in constraint functions or constraint optimization is always the same whenever the subjects are. Uh, we we have to make the subject of lambda from the first equation that we have done, and it is also it is also done similarly with the first one. So after that, we want to make a comparison that lambda equals to lambda, and this is the first equation, and then this equals to the second equation, which is this. So we want to make a P1 over P2, and then we obtain this. And you can do whatever you want. I mean, like, actually, we want to find the variable of x1 or x2. So I found the x2. I mean, like, I would like to find the x2. So here's the x2. After you find the x2, you want to substitute the x2 to the constant function to find the x1. So you know the constant function is given in the it's here. It's this, and then you just simply substitute the x2, the value of the x2, into the constant function, and then you want to break down this multiplication into this, and then you just a simple calculation, mathematical calculation, and then at the end of the day, you found out the x1. How about using the Cobb-Douglas comparison? I mean, like the Cobb-Douglas function. So basically, it's almost similar, but that is different. So the first one is that we know that the given utility function and the subject function or the constant function, and we want to find the marginal utility for x1 and x2. So the marginal utility of x1 is by deriving the I mean, like the what is called the utility function with respect to x1, and this is the result. It's just basically the same with this, but without using the derived constant function, and do it as well as x2. And then we know that the marginal utility, I mean, like the demand function is same. It's just the same. We want to make the comparison of marginal utility x1 equals to marginal utility of x2 by dividing into P1 and dividing into P2. So you just substitute it, and boom, you got P1 over P2. It is similar, or it is the same as, it is the same as the end product of comparing lambda of Lagrange function. So at the end of the day, we can, to determine the constraint optimization, we can use Cobb-Douglas, either Cobb-Douglas or the Lagrange function. So yeah, that is the solution for the question number 2. Let's move on to question number 3. The question number 3 is given that solve the cost minimization problem with this function and this subject function, or we can say that as we can say this as the constant inequal constraint function, where R is a raw material, L is labor, and K capital, and B, C equals to 0, with A plus C, I mean, sorry, A, B, C more than 0, with A plus C lower than 1. Interpret the production function in this problem. So we know the function here, and we, what we want to do is make it into a Lagrange function. Basically, Lagrange, it is almost similar with the Lagrange function of constant function. However, in Kuhn-Tucker condition, you need to adding minus as your multiplication. So you have to distribute the minus of each variables of the function. And for the constant function, you just do the same like Lagrange function, which is distributing the lambda of its variables here. So next, the this the next solution is that we want to make what is that called? Yeah, dou L with respect to labor. So we just can derive it manually or derive it manually, and then the second one is also the same. You can derive it with respect to the certain subject or the certain variables. And oh yeah, don't forget to classify this as first function, second function, and third function. And the last one is for the derivation of L with respect to lambda, which is we know as the constant function, inequal constant function. So after you found out the equations, you want to make the subject of each equation into the lambda. And after you make the subject of, after you making it the equation to the subject of lambda, you want to make it compare of each of its functions. For the first one is function 1 and function 2, because lambda is just it is the same in constraint function or in Kuhn-Tucker condition. We just substitute it. Oh yeah, first you have to do the manipulation in order to obtain this. And then we found that W over R equals to 1 over B. And we want to compare it by the function 2 or the second function with the third function, which is here. We have to manipulate first. Then we obtain this. And the end product is here. But I want to make it linear, but by eliminating, not eliminating, I mean, by changing the denominator as the multiplicator. So we found that R A open bracket L plus BK close bracket equals to V times R times B times C. And it is also the same with the comparison of function 3 and function 1. Basically, yeah, it's just the same as the previous method. You want to manipulate the function, and then we obtain the end product of this calculation, this as this, and you want to manipulate again in order to change the denominator as a multiplicator. Why do we have to do that? So the answer is right here. We did this manipulation to make a simultaneous equation to find the value of L, K, or R. So what I am going to do is that we are subtracting to find the value of R. Yeah, because we can do the simultaneous equation. We subtract it into uh, in this into this, simple calculation, and we want to make another manipulation. What is it? The manipulation is that uh, we want to find the LBK so we can substitute it into the constant function, which is this, and then the next step is the substitute to the constant function. Just substitute it here into here. But still, this is not enough. You have to make R as a subject, so R equals to the given value of the given value or the font value of have we done of what have we done. So the conclusion is, in order to minimize the cost, the R must equal or more than the value, more than the font value or the given value that has been found earlier. Basically, to determine the minimization of the cost, you can use the subject except of R. You can use L, you can use K, but in order to know the solution, I think the one is enough. So I use R as a subject. So you know that the minimization of cost can be done if R is or the raw material is more than the given value. So that is all, guys. Thank you for watching, and I hope you enjoy, and this can be beneficial to your mathematical skills.